What happens when the laws of physics stop adding up? When something in the universe doesn't behave the way every textbook says it should? That's exactly what scientists found with a tiny particle called the Muon. It spins just a little faster than the rules predict. And that tiny difference could change everything we know about how the universe works. Some think it's the first sign of new physics, others say it's just better math. Either way, the question is simple. Which one is true? The muon is almost identical to the electron, just heavier and short-lived.
Why we care about the muon, or first what the muon is, it's exactly like an electron except heavier. That's it.
It exists for only a few millionths of a second before it decays, but in that moment it tells scientists how matter behaves at the smallest scales. When a muon moves through a magnetic field, it spins, like a tiny compass needle tracing invisible lines of force. That spin is described by a number called G. The Standard Model, the framework that describes how particles interact, predicts that value with incredible precision. If the measured number doesn't match, it means something in our understanding of the universe is incomplete. When physicists measured the muon's spin, they found that G wasn't quite what the theory predicted. The difference was small, but it stayed consistent, repeatable, impossible to ignore. That tiny mismatch became known as the Muon G2 anomaly, and it's been keeping scientists awake for decades. To understand how this mystery began, we go back to the 1950s. At CERN, researchers were among the first to measure the muon's magnetic strength. Their results weren't perfect, but they hinted that the muon might be slightly more magnetic than expected. As technology improved, each generation of experiments pushed the precision further, narrowing the margin of error. By the 1990s, the search led to Brookhaven National Laboratory in New York. There, a team built a massive circular magnet where beams of muons raced around at nearly the speed of light. Each time a muon decayed, it gave off a flash of light, and by tracking those flashes, scientists could see how the spins changed over time. After years of measurement, Brookhaven's results were clear that the muon spin was still too fast. The difference was only about 3 parts in a billion, but in physics, that's enough to question everything we thought we knew. When Brookhaven's experiment ended, its 15-meter-wide magnet was shipped across the country to Fermilab in Illinois. It moved by barge, then by truck, a journey that looked almost absurd for something so delicate. At Fermilab, engineers rebuilt it from the ground up, upgraded the detectors, and prepared to run the test again with cleaner Muon beams and tighter precision.
If we see any discrepancy between the two, it must be because there's different types of particles or new physics popping into and out of existence in the vacuum. So it's an indirect way of measuring if there's new stuff and new particles out there in the vacuum.
In 2021, the first results arrived and the wobble was still there. The numbers matched Brookhaven's almost exactly. Statistically, the odds of that happening by random chance were about 1 in 40,000. It wasn't enough to claim a discovery, but it was strong enough to keep the world watching. So now the physics community faces the same question. Is this a crack in the laws of nature, or proof that our math just isn't perfect yet? For many physicists, that small wobble felt like the start of a revolution. If the muon really was spinning faster than it should, it meant something unseen was tugging on it, a new particle or force just beyond our reach. The hunt was on to find out what it could be, but not everyone agreed. Some theorists believed the mystery wasn't new physics at all, just a sign that the calculations behind the Standard Model still weren't perfect. To understand that argument, you have to know what makes this problem so tricky. The Standard Model predicts the muon's G value by combining the effects of 3 known forces: electromagnetic, weak, and strong. The first 2 are straightforward. They can be measured and simulated with remarkable precision. But the strong force, the one that binds quarks together inside protons and neutrons, is a different story. Its math is so chaotic that ordinary equations stop working. Instead, scientists use data and massive computer simulations to approximate it. At first, those approximations looked solid. Then computing power improved, and a new approach called lattice QCD changed everything. In lattice QCD, space and time are represented as a grid, and the interactions between quarks and gluons are calculated point by point. It's slow, it's expensive, but it lets scientists rebuild the strong force from scratch one quantum at a time. As the lattice results got sharper, something interesting happened. The theoretical value of G began to shift closer to the experimental result. Each new calculation trimmed the size of the anomaly, suggesting that what looked like new physics might actually be better math. Still, the story wasn't over. Hidden deep in those calculations were effects so subtle they'd been ignored for decades. One of them is called hadronic light-by-light scattering, a process where photons, the particles of light, briefly turn into quark-antiquark pairs before turning back into light again. It sounds abstract, but it slightly alters the muon's motion. For years, it was one of the biggest uncertainties in the entire equation. Recently, teams combined new experimental data with lattice simulations to finally model that process more accurately. Once again, the numbers inched closer to the standard model's prediction. Each correction made the gap smaller, but not zero. Another overlooked piece came from heavier, short-lived particles called tensor mesons. They don't last long enough to measure directly, but they influence the muon just the same. Until recently, no one could calculate their effect precisely. Now, using improved theoretical tools, even that piece of the puzzle is being refined. Every update narrows the gap, but a small difference remains. This divide has created two camps in physics. One group believes the anomaly is still real, a clear sign that something new is at play, perhaps a hidden family of supersymmetric particles, or a new boson that interacts only with muons. The other group argues that the strong force is simply more complicated than anyone expected, and the standard model will hold once we fully understand it. While the debate continues, Fermilab keeps collecting data. Each new run improves precision, reduces uncertainty, and tests whether the wobble holds. Meanwhile, theorists refine their calculations, checking every assumption that went into predicting G. The stakes couldn't be higher. If the anomaly survives, if the numbers stay apart, even after every correction, it would mean our most trusted theory of matter is incomplete. If the difference disappears, it means we've finally learned to describe nature with unprecedented accuracy. Either way, we win because the chase is forcing physics to reach a level of precision no one thought possible. Around the world, new experiments are stepping in to test the muon's strange behavior from fresh angles. In Japan, at J-PARC, scientists are building a completely different version of the G2 experiment. Instead of using high-speed beams, they'll use ultra-cold muons, slower particles that can be measured with even greater precision. If J-PARC sees the same wobble, it would confirm that the anomaly is real. If it doesn't, the mystery might vanish overnight. Across the Pacific, another project called Bell 2 is searching for rare decays that could reveal whether muons behave differently from electrons. It's a different question, but tied to the same puzzle. Does nature treat these particles equally, or is there a hidden bias built into the laws of physics? Every new data point adds another piece to the map. Meanwhile, theorists continue refining their models. Supercomputers are running larger lattice QCD simulations than ever before, reducing uncertainty line by line. Different research groups now compare results in real time, cross-checking every assumption that feeds into the standard model's prediction for G. The goal is simple: remove every possible doubt. After decades of work, the field is closer than ever to a final answer. If the anomaly holds, if the numbers remain apart, even after all the corrections, it would mean new physics. A hidden force, a new particle, something outside the framework that has guided science for half a century. It would trigger one of the biggest shifts in modern physics since the discovery of the Higgs boson. But if the anomaly fades, if the new measurements fall in line with the standard model, that outcome is just as powerful. It would prove that human precision has caught up with nature's complexity, that we can now calculate the strong force with confidence once thought impossible. In that case, the Muon story becomes a symbol of progress, not mystery.
And so the only way to keep the muons around long enough to make this measurement is to get them going at high speeds Because at high speeds, the muon time dilation makes it so that the muon lives longer. You get relativistic effects that make it so that the muon lives longer according to our clocks.
Either way, the Muon has already changed physics. It pushed experiments to the limits of accuracy, forced theorists to rebuild their tools, and reminded everyone that even the smallest details can shake the biggest ideas. The next few years will decide how this story ends. New data from J-PARC, improved lattice simulations, and cross-checks from experiments like Bell 2 will all converge. If they agree, we'll finally know whether the wobble marks a doorway to new physics or proof that the old rules still hold. Until then, the Muon keeps spinning, quiet but defiant. A tiny particle still daring us to understand why the universe doesn't quite play by its own rules.